Welcome to DAR Tutors for online and home tuition. Today, we're diving into a fundamental concept in statistics, the standard normal distribution. This is a key topic in the IB mathematics analysis and approaches higher level curriculum. By the end of this lesson, you will be able to, first, find the z-score for a value in any normal distribution, which allows for comparisons between different datasets. Second, use the standard normal distribution and a graphics calculator to calculate probabilities. And third, find an unknown mean or standard deviation of a normal distribution using z-scores. Let's get started. Our first objective is to understand z-scores and the standard normal distribution. Let's begin with the standard normal distribution. Suppose we have a random variable x that follows a normal distribution with a mean m and a standard deviation. We can write this as x is distributed as a normal with mean mu and variance sigma squared. To compare values from different normal distributions, which might have very different means and standard deviations, we need a standard measure. This is where the z-score comes in. For any value of x, we can calculate a z-score using this formula. Z equals x minus mu, all divided by sigma. This transformation is called the z-transformation. So, what does this z-score tell us? It tells us the number of standard deviations a particular value of x is away from the mean of its distribution. A positive z-score means the value is above the mean, and a negative z-score means it's below. For example, if ZDL1, the value x is one standard deviation above the mean. If we have a z-score of 1.84, it means the x value is 1.84 standard deviations to the right of or above the mean. Conversely, if we have a z-score of negative 0.273, the x value is 0.273 standard deviations to the left of or below the mean. So the z-score provides a universal scale that helps us understand how a value stands in its distribution. Now let's explore what happens when we apply this z-transformation to every single value in a normal distribution x. It turns out that the new set of z-scores also forms a normal distribution. But it's a very special one. The z-scores will be normally distributed with a mean of 0 and a standard deviation of 1. This special distribution is called the standard normal distribution, or the z-distribution. This is a profound result. No matter what the mean mu and standard deviation sigma were for the original data, their z-scores will always have a mean of 0 and a standard deviation of 1. It normalizes any normal distribution. Let's look at this diagram. On top, we have a normal curve for an arbitrary variable x with mean m and standard deviation c. Below it, we have the standard normal curve for z. Notice how the shape is identical, but the horizontal scale is different. A value of m on the x-axis aligns with 0 on the z-axis because the mean is 0 standard deviations from itself. A value of m plus s on the x-axis aligns with 1 on the z-axis, meaning it's one standard deviation above the mean. This standardization is incredibly useful. Instead of having countless tables for every possible normal distribution, we only need one, the standard normal table. Of course, with modern graphics calculators, this is less about tables and more about a unified method for probability calculations. Let's work through an example to see how z-scores allow us to compare performances that are in different contexts. Consider this problem. Kelly scored 73% in history, where the class mean was 68% and the standard deviation was 10.2%. In mathematics, she scored 66%, where the class mean was 62% and the standard deviation was 6.8%. In which subject did Kelly perform better relative to her class? If we just look at the raw percentages, % is higher than 66%. But this doesn't tell us how challenging each exam was. To find that, we need to compare her scores using z-scores. Let's calculate her z-score for history. The formula is z equals score minus mean, divided by standard deviation. Plugging in the values, we get 5 divided by 10.2, which is approximately 0.49 nu. This means Kelly's history score was 0.49 standard deviations above the class mean. Now let's do the same for mathematics. Here her score is 66, the mean is 62, and the standard deviation is 6.8. Calculating this, we get 4 divided by 6.8, which is approximately 0.588. This means Kelly's math score was 0.588 standard deviations above the class mean. Now we can compare the z-scores. 0.588 is greater than 0.490. Although her percentage was lower, Kelly's mathematics score was better compared to the rest of her class because it was further above the mean in terms of standard deviations. It tells us she was more outstanding in math. Let's look at a similar example, this time involving swimming competition times. Frederick competed in several swimming events. Here are his times, the event means, and standard deviations. We need to find his z-scores and then determine his best performance. We also need to think about what a z-score means in this context. For most things, like test scores, a higher score is better, which means a positive z-score is better. But for races, a lower time is better. This means a good performance will have a time below the average, resulting in a negative z-score. So for this problem, the lower or more negative the z-score, the better Frederick's performance was. Let's calculate the z-score for his 50 Miller freestyle time. That's 32.1 minus 27.8 divided by 2.2, which gives us 4.3 over 2.2, or approximately 1.95. This is a very poor result. He was nearly 2 standard deviations slower than the average. Now for the 100 meter backstroke. The time is 53.5, the mean is 58.1, and the standard deviation is 4.3. This gives us 4.6 over 4.3, which is about negative 1.07. This is a very good result. He was more than 1 standard deviation faster than the average. Let's say we calculated the z-scores for all events and got these values. We have 1.95 for freestyle, 1.07 for backstroke, 0.58 for breaststroke, and 0.35 for butterfly. Remember, for swimming, lower is better. So we are looking for the most negative z-score. Comparing these, 1.07 is the smallest z-score. Therefore, Frederick's best performance was in the 100 meters backstroke. This shows that the context of a problem is crucial when interpreting z-scores. Now that we understand how z-scores work, let's move on to our second objective. Using the standard normal distribution to calculate probabilities. Calculating probabilities using the standard normal distribution. The most important property of z-scores is that any probability question about a normal random variable x can be restated as a probability question about the standard normal random variable z. For example, the probability that x is greater than some value x1 is exactly the same as the probability that its corresponding z-score, z1, is greater than or equal to z1. Here z1 is simply x1 minus mu divided by sigma. Let's visualize this. On the left, we have a normal curve for x, and we want to find the area to the right of x1. This area represents the probability. If we transform this to the z distribution on the right, the area to the right of its corresponding z1 is exactly the same. We've just changed the scale on the horizontal axis. The same principle applies for other types of probability statements. The probability of x being less than or equal to x1 is equal to the probability of z being less than or equal to z1. And the probability of x being between two values, x1 and x2, is equal to the probability of z being between their corresponding z-scores, z1 and z2. This means that if we can calculate the z-score, we can use a graphics calculator to find the probability, no matter what the original mean and standard deviation were. Let's work through an IB-style problem to solidify this concept. Suppose the height of students in a school is normally distributed with a mean of 160 centimeters and a standard deviation of 8 centimeters. So we can write x is distributed as a normal with mean 160 and variance 8 squared. Part A asks for the probability that a randomly selected student is taller than 175 centimeters. This is P of x is greater than or equal to 175. First, we find the z-score. Z equals 175 minus 160 all over 8. That's 15 divided by 8, which is 1.875. So the problem is equivalent to finding P of z is greater than or equal to 1.875. We can find this using our graphics calculator. On the normal CDF function, we input 1.875 as the lower bound, a large number like 1e99 as the upper bound, a mean of 0, and a standard deviation of 1. The calculator output gives us approximately 0.030. Part B asks for the percentage of students between 150 and 170 centimeters tall. We need to find P of X is between 150 and 170. We need to calculate two z-scores. For 150, z1 is negative 1.25. For 170, z2 is 1.25. The probability is P of z is between 1.25 and 1.25. In the calculator, we use normal CDF with a lower bound of 1.25, an upper bound of 1.25, mean 0, and standard deviation 1. The result is approximately 0.788. To convert this to a percentage, we multiply by 100, which gives us 78.87%. We've learned to find a probability given an x value. Our third objective is the reverse, finding an x value given a probability. This is called finding a quantile. Finding unknown values, quantiles. A quantile is simply the value below which a certain percentage of the distribution lies. For instance, the 95th percentile is the value k, such that 95% of the data is less than k. This process is the inverse of what we did before, so we use the inverse normal function on our calculator, often labeled InVNorm. Let's revisit the crab example. The shell length of crabs, x, is normally distributed with a mean of 70 mm and a standard deviation of 10 mm. A biologist wants to allow only the largest 5% to be harvested. What is the minimum length for a crab to be harvested? If the largest 5 part can be harvested, it means that 95% of the crabs are too small. We are looking for the value k such that the probability of a crab being smaller than k is 0.95. Our task is to find k such that P of x is less than or equal to k equals 0.95. Most calculators require the area to the left, which is perfect here. We use the InVNorm function. We input the area to the left, which is 0.95, the mean of the distribution, which is 70, and the standard deviation, 10. The calculator gives us approximately 86.45. So, the minimum length for a crab to be harvested is 86.45 mm. This diagram shows what we've calculated. 95% of the curve's area is to the left of k, which is our 95th percentile. This corresponds to the threshold for harvesting. Let's work through another quantile problem, this time with a right-tailed probability. Suppose the volumes of cool drink in bottles filled by a machine are normally distributed with a mean of 503 mmol and a standard deviation of 0.5 mmol. Bottles are rejected if they are overfilled, and 2% are rejected this way. What is the maximum volume a bottle can contain to be kept for sale? If 2% are rejected for being overfilled, that means their volume K is in the top 2% of the distribution. We are looking for the value K such that the probability of a bottle having a volume greater than K is 0.02. We need to find K such that P of X is greater than or equal to K equals 0.02. As mentioned, most calculators require the area to the left. If the area to the right is 0.02, then the area to the left is 1 minus 0.02, which is 0.98. So we need to find the 98th percentile, the value k such that P of x is less than or equal to k equals 0.98. Using the inverse normal function, we input an area of 0.98, the mean of 503, and the standard deviation of 0.5. The calculator gives us approximately 504.03. This is the 98th percentile. Any bottle with a volume larger than 504.03 ml is rejected. Therefore, the maximum volume allowed is 504.03 ml. Here's the visual. The shaded area in the right tail represents the 2% of overfilled bottles. The area to its left, covering the acceptable bottles, is 98%, which is the value we use in our calculation. We now come to our final objective, finding an unknown mean or standard deviation of a normal distribution. This type of problem might seem difficult, but the strategy is quite clear. We always need to convert the x values and probabilities into z-scores using the standard normal distribution. By doing this, we transform the problem from one about a generic normal distribution x to one about the standard normal distribution z, for which we know the parameters, mean 0 and standard deviation 1. Let's take a common scenario. You have information about two quantiles of a distribution, and you need to find the mean and standard deviation. Consider a random variable x that is normally distributed with an unknown mean mu and standard deviation sigma. We are given that the 10th percentile is 20, meaning p of x is less than or equal to 20 equals 0.1. We are also given that the 85th percentile is 29, meaning p of x is less than or equal to 29 equals 0.85. Let's convert these statements into equations involving z-scores. First, for the 10th percentile, we find the z-score. Using inverse normal on our calculator with an area of 0.1, a mean of 0, and standard deviation of 1, we get a z-score of approximately -1.282. Using our z-score formula, we get the equation -1.282 equals 20 minus mu divided by sigma. Rearranging this gives our first equation, 20 minus mu equals -1.282 times sigma. Next, for the 85th percentile, we find its z-score. With an area of 0.85, the calculator gives us approximately 1.036. Similarly, we form our second equation. 29 minus mu equals 1.036 times sigma. Now we have a system of two simultaneous equations with two unknowns, mu and sigma. We can solve these using substitution or elimination. Subtracting equation 1 from equation 2 is a good strategy. 29 minus 20 is 9. Negative mu minus negative mu is 0. 1.036 sigma minus negative 1.282 sigma is 2.3118 sigma. So 9 is approximately equal to 2.318 sigma. Solving for sigma gives us approximately 3.8. Substituting sigma back into equation 1, we can find mu. 20 minus mu is approximately -4.97. This gives us a mean mu of approximately 24.97, which we can round to 25. By using z-scores, we successfully transformed a complex problem into a solvable system of equations. Okay, let's recap what we've learned today. We started by defining the z-score as the number of standard deviations a value is from the mean. We then saw how applying this z transformation to any normal distribution n of mu, sigma squared, results in the standard normal distribution n of 0, 1 squared. This standardization allows us to use a single tool, a calculator's normal distribution functions, to solve all types of problems involving normal distributions. We covered 3 key applications: finding probabilities from x values using normal CDF, finding x values from probabilities using NV-norm, and the more advanced technique of finding unknown means or standard deviations by setting up simultaneous equations. To test your understanding, we have 5 IB-style practice questions for you to work through. Pause the video now and attempt them. Solutions will follow. Here are your practice questions. Work through them step by step. Welcome back. Let's go over the solutions to the practice questions. Question 1 asks for the probability that x is between 70 and 95. We use normal CDF with a lower bound of 70, an upper bound of 95, the given mean of 80 and standard deviation of 12. The result is approximately 0.697. Question 2 asks for the 90th percentile. We use NV-norm with an area to the left of 0.90, mean 100, and standard deviation 15. The calculator gives us approximately 119.2. So, an IQ of 119.2 represents the 90th percentile. For question 3, percent of nails are too short, which means we are looking for the first percentile. We use NV-norm with an area of 0.01, mean 50, and standard deviation 0.5. The answer is about 48.84 millimeters. This is the minimum acceptable length. Question 4 involves finding the mean. We're given that the probability of a bag weighing less than 495 Gs is 0.05. We first find the corresponding z-score using NV-norm for a standard normal distribution. This is about 1.645. We then set up and solve the z-score formula to find the mean, which is approximately 496.97 at Shijai. Finally, for question 5, we use the 2 quantile approach. P of x less than 250 is 0.15, so z1 is about 0.36. P of x greater than 400 is 0.25, which means P of x less than 400 is 0.75, so Z2 is about 0.674. This gives us two equations. Solving them simultaneously by subtraction gives sigma is approximately 87.79. Substituting back, we find mu is approximately 340.13. I hope this video has helped you solidify your understanding of the standard normal distribution and its applications in IB/AAHL maths. Thank you for watching.